Okay, let's talk about some basic probability rules now. And as I mentioned earlier, the concepts of mutually exclusive versus non-mutually exclusive, dependent and independent events will play again an important role here. So here you have essentially a decision tree for when to use different kinds of probability rules. And it basically starts with you asking a question. And whenever the question involves an or, then you know we are dealing with an addition rule. So, and once you know that my question is something like what's the probability of this or that, then the next question is, are the events mutually exclusive or are they not mutually exclusive? When the events are mutually exclusive, like for example, you roll a die and the question is what's the probability that you roll a 1 or a 2? So then we know, okay, the question is about an or, so that calls for the addition rule, but rolling a 1 or a 2, those are mutually exclusive events. You cannot roll both at the same time. So therefore we just add up the individual probabilities. And the correct statistical language is the probability of A union B. So this sign is actually without. So this means in statistical language union, but most people will say, you can also say or. So the probability of A or B, but technically correct would be A union B, is the probability of A plus the probability of B. Okay, but if your events are mutually non-exclusive, like what's the question that when you roll a die that you get something which is less than 5 and odd, so that can happen at the same time. So then we have to use the formula, the probability of A union B or A or B is the probability of A plus the probability of B minus the probability of A and B. Well, so this sign, that means in statistical correct terminology, it would be intersection. But, you can also say and I think that is probably more commonly used. But the correct term is intersection. So in other words, if we have mutually non-exclusive events, like what's the probability that when you roll a die you get a number less than 5 or an odd number, well, then, then if we don't subtract the probability of being odd and less than 4, we would double count them in those individual probabilities. So therefore the probability of A or B for mutually non-exclusive events is the probability of A plus the probability of B minus the probability of A and B. And again, that takes care to avoid double counting. Okay, so whenever you hear in a question, what's the probability of this or that, you know immediately we are dealing with an addition rule. Well, you could also hear in a question, what's the probability of this and that? And whenever you hear this and that, you are dealing with a multiplication rule. And when it comes to multiplication rule, what matters are the events independent or are they dependent? If they are independent, like, I want to know what's the probability that when you roll a die twice, that in the first roll you get a 6 and in the second you get a 6. Well, rolling a 6 on the first row doesn't take away the probability of rolling a 6, or doesn't affect the probability of rolling a 6 again. So that would be 1 over 6 times 1 over 6, or 1 over 36. But if the events are dependent, then that is the case of drawing without replacement. And then we would say, okay, dependent events are the probability of A and B, that is equal to the probability of A times the probability of B given A. Okay, so let's just do some examples and let's actually calculate some probabilities. So let's start with the addition rule for mutually exclusive events. So what's the probability of rolling a 1 or, again, so this is or, that tells you, okay, this is decision, this is the addition rule. And then we say the probability of a 1 union 2 is equal to the probability that you get a 1 plus the probability that you get a 2, 1 over 6 plus 1 over 6, 2 over 6, or 1 over 3. Then the next one is, for mutually non-exclusive event, what's the probability of rolling a number less than 5, or an odd number, odd, in a single die roll? So the probability of less than 5 union odd is the probability of less than 5. Okay, so that's 4 over 6, plus the probability of odd, well, 1, 3, or 5, so that's 3 over 6. But now we counted the 1 and the 3, which are both less than 5 and odd twice. So we have to subtract it again once. So we get 4 over 6 plus 3 over 6 minus 2 over 6 equals 5 over 6. Okay, so that's basically the addition rule. So now let's move to the multiplication rule. What's the probability of rolling 2 consecutive 6s in 2 rolls? It's the probability of 6 and another 6. And we just multiply the probability, so that's 1 over 6 times 1 over 6 equals 1 over 36. But what if the events are dependent on each other? So consider the example that we have a cookie jar. And let's say in that jar we have 3 vanilla cookies and we have 2 chocolate cookies. So then we would say, if we want to know what's the probability that the first one is a chocolate cookie and the second one is a chocolate cookie. So then in the first draw without replacement, there are 2 chocolate cookies, so that's 2 over 5. But now 1 chocolate cookie is gone, and in the second one, so the probability that the second is a chocolate, given that the first one was already a chocolate cookie drawn, that leaves us with 1 over 4. And then we have 2 over 5 times 1 over 4, which is 2 over 20, or 1 over 10. Okay, so the multiplication rule can also be used for independence tests, and that's actually an important field. And so let's just consider independence test. So what we have is a survey of 100 students, and they revealed the following. 90 said that they regularly attended class, and 70 of those who regularly attended class passed the exam, and 10 said that they did not regularly attend the class. And out of those who did not regularly attend class, 8 passed the exam. Okay, so now here we have a crosstab, which we already have discussed earlier. in the context of descriptive statistics. So now let's fill out this crosstab, and what you can see is this crosstab has inner cells and outer cells. The outer cells are overall probabilities, the inner cells are conditional probabilities. Okay, so let's start with how many students attend regularly class. Well, that's 90. So we have here 90. Well, that implies, because we had 100 in total, that means 10 must not have attended class regularly. Okay, so now we can say that the probability that the randomly selected student is a regular attender, the probability of A, well, that's 0.9. And the probability that a randomly selected student is not a regularly attender, so that's the complement, it's the probability of A prime, so that's 0.1. Okay, so next we need to know how many students out of the 100 did succeed. So 72 of those who regularly attended passed the exam, and 8 of those who not regularly attended also passed. So a total of 80 passed or succeeded. Well, that means that 20 did not pass. So we know that because we have a total of 100. And so now we know the overall probabilities that a randomly selected student may be a succeeder or someone who passes the exam, that's 80%. The failing rate that a randomly selected student from the entire population does not succeed is 20%. The probability that someone attends regularly is 90%. And the probability that a randomly selected person from the population does not regularly attend is 10%. So those are overall probabilities. Those are not conditional probabilities. The conditional probabilities are now those inner cells. So now we want to know what's the probability, maybe let's give it a different color. So what's the probability that among the 90 people who regularly attend, how many of those pass? Okay, so that's 72. 72 out of the 90 who regularly pass the exam. 72 of those who regularly attended passed the exam. So now what we need to do is calculate the conditional probability. What's the probability that somebody succeeds given, this vertical bar means given, that somebody attends? Well, that's basically a ratio. The probability, the people that attended, that's a total of 90, and 72 of those passed, so that probability is 80%. Okay, so that's this one. Well, then that implies that 20% of those who regularly attend did not pass. So we can write the probability of no success as prime, given that they attend. So that is 18. And that is then 18 over 90, which is 20%, or 0.2. Okay, so now we are done with these. Next, what's the probability that a non-attender, so now we are concerned with given that somebody does not attend, and there are a total of 10. And how many of those did succeed? Well, that's 8. So the probability of success for a non-attender A prime is 0.8. And that means that 20% of those who do not regularly attend, they fail. So that is no success S prime, given that they do not regularly attend A prime. That is 2 over 10, which is 20%. Okay, so now we want to know, is attendance and success, are they dependent or independent? Well, intuitively we would think that those are dependent events. Presumably attending class increases the likelihood of success. But if we look at this data, the probability of a student succeeding is 0.8. And the probability of a student who attends, which is the probability of success given that they attend, well, it's also 80%. So it doesn't really make a difference whether somebody attends or not. It's the same probability. And also the probability of success given that they do not attend, well, that's also 0.8. Probability of success given that they do not attend, that's also 0.8. So now we can use the relationship between the overall probability and the conditional probability. If they are the same, then the events must be statistically independent from each other. Okay, so those are the independent tests, and let's just do another example on the next slide. But now we need to fill out everything ourselves. Okay, so let's just go through it. A survey of 100 students revealed the following. 80 said that they regularly eat fast food. Okay, so the fast food eaters, it's a total of 80. And a total of 100 students were surveyed. So now we know the probability of a fast food, FF, eater is 0.8. The probability that somebody is not a fast food eater must then be 20, or 0.2. So next is how many people report stomach pain. Well, 56 out of those who regularly eat fast food report stomach pain. Okay, so fast food eater, yes, stomach pain, 56. And 4 of those who do not regularly eat fast food no, also report stomach pain. So that's a 4. So that means here we have 60. And that implies that 40 must not have reported stomach pain. You can see this logic is a little bit related to the degrees of freedom concept. If we know one, we automatically know the other. So that means the probability that a randomly selected person from the population has stomach pain is 0.6. And the probability that somebody has no stomach pain, SP prime, is 0.4. Well, if we have a total fast food eater of 80, of which 56 reported stomach pain, well, 24 must have reported no stomach pain. And of the 20 no fast food eaters, 4 reported stomach pain. That means 16 did not have stomach pain. So now we can calculate the conditional probabilities. So what's the probability that somebody has stomach pain given that they are fast food eaters? Well, the total probability, or there are like 80 fast food eaters and 56 report stomach pain. Well, that's 56 over 80, so that's a probability of 70%. So 0.7. Well, that means that the probability that somebody who eats regularly fast food has no stomach pain occasionally is stomach pain prime. And now here we have 24 over 80, which is 0.3. Okay, so next, what's the probability that among those who are not regularly fast food eaters, so FF prime, of which we have a total of 20, that somebody has occasionally stomach pain? Well, that's 4. So now we have 4 over 20, which is 0.2. Okay, and that means that those who do not regularly eat fast food, FF prime, how many of those, what percentage of those have no stomach pain, SP prime? Well, that is now 16 over 20. Which is 0.8. Okay, so now we have everything, so now we can calculate again, now we can conduct again an independence test, and let's say we want to know whether the probability of a person reporting stomach pain from the entire population is 0.6. And what's the probability that somebody has stomach pain given that they regularly eat fast food? Well, that is 0.7. And so that is obviously much greater. So now we have statistical evidence in favor of supporting the idea that regular fast food consumption increases the likelihood of somebody having stomach pain. Right. So in this case, and of course there is still here, so here we have to say success and attendance, that's still from the previous. So here we need to say stomach pain and fast food consumption are not independent because the probability of stomach pain is greater, actually. So the probability of stomach pain, given that they are fast food eaters, is greater. So the probability that a randomly selected individual has stomach pain occasionally is 0.6, but that is less than the probability that somebody has stomach pain given that they given that they regularly consume fast food, that's 0.7. So this result suggests that the consumption of fast food and stomach pain are probably not independent, and that must then be used in order to investigate further. But such independent tests, they are very important. And so just imagine that you have, for example, a pharmaceutical company that has introduced a new medication against some ailment, and now people consume that medication, And let's say people complain that they have a headache after taking that pill. So now they may sue the pharmaceutical company, and now the pharmaceutical company, they need to basically prove that the taking of the pill or the new medication and the headache, those are independent events. So now what they try to do is to find the probability among the population that takes that pill, how often people report headache. And if that probability is statistically significantly greater than any person in the population reporting, occasional headaches, then the events would be dependent. And of course, what the pharmaceutical company is trying to find out is that the probability that a randomly selected person from the population, whether they take that medication or not, has the same probability of reporting occasional headaches than those who take the pill. So there are like lots of applications for those independence tests in all kinds of applications, like pharmaceutical tests for negative consequences or side effects of certain pills. Okay, so I hope it is clear how independence tests work. And let's just stop here and then let's talk about Bayes' theorem in the next video.